Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. Pray you help us use this time wisely, Lord, to glorify you what we do, Lord. In your name I pray. Amen. So I'll talk about partial differential equations for a little while, then I'll take your homework questions towards the end. So what is a partial differential equation? Kane, could you hit the lights for a second here? Just half of them, the front. That's good. A partial differential equation is something that involves partial derivatives. So the ones we're going to learn how to solve in here are the following. The heat equation, which is something like uxx, here's just an example of one, 3ut. We'll learn how to solve the wave equation. The wave equation is something like uxx equals to 3utt. These are just specific examples, all right? And then we'll also learn how to solve Laplace's equation. Laplace's equation is uxx plus uyy equals to 0. So these are partial differential equations. Like the notation ux means partial u partial x, and uxx would be like the second partial derivative with respect to x, and so forth. And we're going to solve these partial differential equations subject to what are called boundary conditions, all right? And it's kind of an interesting story. So the start of this story is we need to learn how to solve what are called boundary value problems, all right? So these notes I've written for you guys are written partly in the interest of making your life easier. So I have to start with telling you how we solve boundary value problems. And in particular, I'll use the projector here, otherwise I would spend about 20 more minutes of class. So I'm creating homework time for you right now, believe it or not. This I would usually belabor much longer. You can go back and look at last year, you'll see. But here we go. So here's the question. Which values, come on, of k, shake some ions loose here. Which values of k, oh man, come on, it's like a DC movie, allow solutions of, there we go, come back to us, Affleck, let's see here, y prime prime, dang it, fine, I'll have to go to, this was come to. So this won't let me in. There we go. So which values of k are allowed, which give us solutions to y prime prime plus ky equals to 0. And we're looking for solutions that satisfy y of 0 is equal to 0 and y of L is equal to 0. You see the difference between that and problems we saw before? Before, I told you like y of 0 is whatever, y prime of 0 is whatever. We can solve that. That's an initial value problem. The difference here is I'm prescribing values of the solution at different independent variable values, 0 and L. So we suppose x is the independent variable, and we're seeking solutions that exist between 0 and L. So there are three cases. K could be 0, k could be positive, k could be negative, right? K is a real number. Those are your choices. If k is 0, y prime prime equal to 0 has a solution y equals to ax plus b. Plugging in 0 gives me b is 0, but then plugging in L gives me AL is equal to 0. So what do you know? We just get A is 0, B is 0, so only the 0 solution is there. This is not interesting. If k is less than 0, that means that we can write k is equal to minus beta squared, and we'd be facing y prime prime minus beta squared y equals to 0. What's the general solution to that? Cosh's and Sinch's of beta x, right? So we get A equals cosh beta x plus B sinh beta x. Y of 0 being 0 gives us that 0 equals to A, because cosh of 0 is 0, and sinh of 0 is, cosh of 0 is 1, sinh of 0 is 0, right? So that gives me the equation A equals to 0, which gives, of course, A is 0. And if you plug in L, that gives me B sinh beta L equals to 0, right? But the thing about sinh is, it's only 0 when you plug in 0. This is if you study the hyperbolic sign, this forces then B to be 0 if L is not 0. We already assume beta is not 0. So consequently, there is no interesting solution in the case that k is less than 0 here. So we can rule out that case. So apparently, to get an interesting solution to this boundary value problem, we have to have that k is positive, which is to say that we can write k as beta squared. So we got y prime prime plus beta squared y equals to 0. So solutions of that are what? Well, we learned this at the start of the course. Solutions have the form a cosine beta x plus b sine beta x, right? I plug in y of 0. Y of 0 gives me the cosine of 0 is 1, sine of 0 is 0, right? So this gives me the condition a times 1 equal to 0, so a is 0. When I plug in y of l, this gives me b sine beta l equal to 0. What does this do? This forces either this to be 0, which is boring because that just gives me the 0 solution, right? Or sine of beta L has to be 0. How can we have sine of beta L be 0? What does that force beta L to be? Not 0. Well, 0 is one possibility, but that particular possibility is not allowed because we assume beta is positive. And L is not 0. What's that? Pi. That's another possibility. Be greedier, though. All solutions. N pi. Right? Any integer multiple of pi, except for 0, will work. 0 doesn't work because I can't have 0 equals to, I can't have 0 here because beta and L are non-zero. Right? So you can't have 0 equals non-zero. But any multiple of pi will work. And, but in fact, since we assumed that beta was positive, we just look for positive integer multiples of pi. So pi, 2 pi, 3 pi, 4 pi, 5 pi, so forth. In summary, this is what we found. If we want to solve this boundary value problem, y prime prime plus ky equals to 0, subject to y of 0 is L, y of 0 and y of L is 0, the solutions have the form y sub n equal to b sub n sine of n pi x over L. That's it. Now this is weird, right? Because this says that for certain values of k, there are no solutions. Right? I don't typically, up to this point in the course, I give you a differential equation. Is there a solution? Yeah, there's a solution, right? But here we're now asking questions which are kind of like, they're the differential equations equivalent of asking like a geometric, you could ask a geometric question. You know, here's these 4 points. Find a circle through these 4 points. Is that a reasonable question? Is there a circle through any 4 points? No. How many points determine a circle? I don't know. Interesting question, huh? But that would be a similar question to this. See, the questions we've been given up to this point is we're like given data at one point. So we're like, where is it? What's its slope? What's its concavity? What's its past concavity? These things we're ascribing at one point. So we can fit a curve which satisfies that data. Now we're trying to make like, it's kind of like group work. You're trying to get 4 people work together on one thing according to a common schedule, each doing work. Probably this is a better picture of group work. So, am I right? Yeah, I'm right. I know you know I'm right. I see here. The other kind of problem we can solve, I mean, there's. Sorry. So if you think about this, there are, let me write down you can turn the lights on for a second, King. So I'm studying, of course this is marker, y prime prime plus ky equals to 0, subject the boundary conditions below. So we have y of 0, y, these are the, I'm sorry, I eventually organized my, oh man, this is worthless, this marker. So we have, on the one hand, case 1 is y of 0 is y of L is equal to 0. That one I just derived for you guys. Sad. Case 2 is, this one's not much better, y prime of 0 equals to y prime of L equals to 0. Right, that's the second proposition in my chapter, or whatever this is, 10, 8, oh, chapter 8. 3 and 4, what are the other possibilities? These are called homogeneous boundary conditions. what's the other possibilities you could imagine facing? You could have like y of 0 was 0, and y prime of L was 0. Or you could even have y prime of 0 is 0, and y prime of L was, I'm sorry, y prime of 0, y of L is 0. These are the sort of 4 generic homogeneous boundary conditions. And these ones we can solve through pretty similar arguments. All right? My point to you so far is that in case 1, we just get signs, right? In case 1, we get signs. We get signs. And k is equal to what? We figured out that k was equal to n squared pi squared over L squared, right? Next, I do the derivatives are 0 at the endpoint, right? Work that out. Again, there are 3 cases. In this case, the 0th case gives you one interesting thing. The constant solution is interesting. Constant solution has derivative 0 at both endpoints, but it's non-zero possibly, right? Like I could have u equals, or I could have, y equals to 1. That would solve case 2, right? Y prime of 1 is 0, y prime of L 0 for the constant function 1. So k equals 0 does contribute something interesting. But again, k less than 0 does not give us anything interesting. And we're put into case 3. And this time, we end up selecting the cosine term. We still get that k is equal to n squared pi squared over L squared. We get cosines. And k is still n squared pi squared over L squared. Like that. Okay. And the analysis is very similar. Then, mixed endpoints, a little bit more interesting. You end up getting, see the k ends up being a little bit weird. Pi squared over 2n minus 1 squared over 4l squared. So we get like odd square divided by 4l squared multiples of pi squared for our k. And we get signs of those. It's kind of surprising. And then in the other mixed endpoint case, we'll get cosines of things like that. All right? Don't even write it down. It's in the notes. You can look it up if you need to. Mostly, we're going to see case 1 and case 2 in the problems we solve, okay? So, you put this away. So let's look at the heat equation. Now I'm going to look at a somewhat generic heat equation to start with here, and I'll try to explain what we're doing. This actually is the whole genesis of the method. This was studied by, among others, but certainly Fourier in the early 19th century. And the method I'm about to show to you is more or less what he did. So we're trying to solve the following problem. Uxx, all right, is equal to alpha u sub t, where alpha is a given constant. All right? And this equation, this partial differential equation, what it does is it models heat flow on a rod. And we're going to try to solve this for 0 less than or equal to x less than or equal to L. All right? And here's a picture of what we're doing. So you got this rod, and if you take a particular point on it, and so here's x equals to 0, here over here is x equals to L, right? And so at x, right here, u of x comma t, this is equal to the temperature at time t at position x. What that equation says is that the flow of heat is proportional to the temperature, right? It says that the temperature is changing in x proportional to how it's changing with time. And this is more generally what's known as a diffuse, I can't say this word. Here, I'll write it out. Diffusivity relation. It describes how, if you think about it, if you heat up one end of a metal rod, right, what happens is the molecules bump into each other, right? And as they hit the ones next to them, that thermal motion, which we interpret as temperature, right, random thermal motion of material particles gives rise to the phenomenon of temperature. And as that propagates across, you get the whole rod is increasing in temperature, right? This is what we sometimes refer to as the conduction of heat. Well, this partial differential equation describes the conduction of heat in a rod. That's why this is called the heat equation. Okay, so that's the physical setup for this problem. And then you can add details, right? You can add boundary conditions to it. The two boundary conditions we're most interested in, the one would be, putting both endpoints of the rod to a fixed temperature. So we could put ice bath here, and we could put an ice bath over here, which would do what? That would fix the temperature at the end of the rod to something constant. All right? We'll make that constant be 0. So with an ice bath, we can make u of 0 be 0, and we can make u of L be 0. And to be more specific, I should really say u of 0t, 0, because u is a function of both x and t, right? So u of L comma t equals to 0 for all t. A question? No? Okay.
You're trying to figure out what it said at the end instead of ice bath.
Oh, yeah, ice bath, yeah. It's not ice baby. But not that be said. Let's see here. Bath. Careful. Careful what I say in here. Now, the other thing you could do would be to put insulators. Ooh, this is nice. That marker's amazing. Insulators, and that would be something like partial u, partial x, 0t equals to 0, and partial u, partial x at L comma t equals to 0 for t greater than 0. That would be if we insulated both endpoints so no heat can flow out of the endpoint. The way to describe that mathematically is to say that the derivative of u with respect to x at the endpoints is 0 for all time. This would be insulated. And then, of course, you could mix, right? You could do insulate one end, put an ice bath on the other, or vice versa. And that brings us to those 4 conditions over there that I've solved the math of. Now, you'll notice that the thing I did at the start of class doesn't really require any partial differential equations, does it? Like, everything we did over here is just the first part of the course and a question we didn't bother asking. Like, what if you get data at different times or different x's, right? We could have done this week 2 in here. Just the same. So this is the method of Fourier then. So here's Fourier's idea. Look for solutions of the form u of x comma t equal to x of x, t of t. Suppose that you can write a solution as an entering sort of gambit here, entering shot, if you will, at trying to solve this thing. Look for solutions which are a product of x and product, just a function of x and just a function of time. Now, if you did have this, if we take partial derivatives, how does it work out? Like, what's ux? Partial x of big X times t, right? But if t is just a function of t, then this is just partial x times t. But without ambiguity, we can just express that as x prime t. Okay? Where it's understood that x prime is differentiating the x function with respect to x. And vice versa, if we calculate, well, what if we calculate uxx? What's that going to work out to? The t pulls out, and we just get x prime prime t, right? How about if we take t derivatives? How's that go? Now, x is a constant with respect to that differentiation, so we can pull the x out, and we've just got x partial t partial t. Notice that big T versus little t. Big T is temperature, little t is time. Well, t is not temperature. T is just the time function, actually. Temperature is the u. Let me not say that. Oops. I mean, you could give whatever kind of units you wanted to either x or t. You can always shift the dimensional constant between the product functions, one or the other. So they don't have independent physical significance, at least in my thinking. X and t are just devices to create a solution at this moment. But that's supposed to be a big X, if you're wondering. These were all big X's. And of course, that's big X, t prime. Okay, now that we have the partial derivative settled, we plug our template solution into the heat equation. If uxx, right, is going to be equal to alpha u sub t, we need what? We need x prime prime t, right, equals to alpha xt prime. So far, so good? Now, then we just isolate the big X and isolate the big T. I'm going to leave alpha with the T because that makes it a little bit prettier. But this gives us x prime prime over x equals to alpha times t prime over t. And here I'm assuming what? X and t are non-zero. We're looking for non-zero solutions to this problem, so that's not a deal breaker. Now at this point, we have to think. All right, so here's the thing. This is a marker which does not work. Man, I can't even hit it from 5 feet away. It's ridiculous. It's catching, isn't it? This is a function of x. This is a function of t. So, I mean, this would tell you, for example, that partial t of x prime prime over x is equal to 0. And this would tell you partial x of alpha t prime over t is equal to 0. Oh, I think I've done it exactly in the uninteresting way. X t. Right? Look, see what I'm saying? If this is just a function of x, right? And this is just a function of t, that means that when I differentiate the left-hand side with respect to x, it's just a function of t, so its derivative is 0. Does that make sense? On the other hand, if I differentiate the right-hand side, it's just a function of x. These are equal, right? It's just a function of x, so its partial derivative is 0. What does this say about both of these ratios? Neither of them can be interesting functions of x or t. What does that leave you with? A constant, right? So thus, x prime prime over x is equal to a constant, which I'll call minus k, and that's, of course, equal to alpha t prime. Excuse me. Goodness gracious. Yowzers. Does that make sense? Now, you ask, why did I put minus k there? Can you see why I did that? So we face x prime prime plus kx equals to 0, and t prime equals to, looks like minus k over alpha t. But I've already been, at the start of this lecture, developing technology to solve these kinds of problems. Right? That's why I made k minus k, so it matches up with my proposition. Yeah? Oh, okay. Now, the time equation, that I can solve directly. So let me call this 1. Let me call this 2. We'll solve 2 to start with. So to solve 2, that's easy. That's dt equals to minus k over alpha t. What's that half solution? That half solution t of t is equal to e to the minus k times little t over alpha. That's a constant coefficient first order differential equation. What is the character? I mean, look, guys, if you don't see what I just did, all I did was, what's the characteristic equation here? It's lambda equals to minus k over alpha. Game over. The solution is this, using our constant coefficient stuff, right? Or if you must, you can separate variables, integrate both sides, get logs, then solve for the variable if you want. Whatever floats your boat. Now we have to make a choice. Are we going to work on the ice bath problem, or are we going to work on the insulator problem? I vote we work on the ice bath problem to start with. So ice bath. What's that say? In other words, u of 0 comma t equals to 0, and u of L comma t equals to 0. The neat thing is that if we study these and feed them to the product solution, we get the same boundary value problems for our x function. For this, you could call this the spatial, not like special, but like Southern special, but this is the spatial solution, as in spatial solution. The spatial solution will satisfy the same boundary value conditions as does the temperature function itself. Here, this is what? This is x of 0, t of t equals to 0, and x of L times t of t equals to 0. Those hold for all time. You notice that the temperature function is non-zero, right? So since those hold for all time, I mean, this then implies that we have x of 0 equal to 0 and x of L equals to 0. So we're back to proposition 1 in my chapter 8. We've got a boundary value problem for the x for the spatial function with vanishing boundary and vanishing well, you guys will remind me. So let's get to it. So we need to solve x prime prime plus kx equals to 0, subject to what? X of 0 is 0, and x of L equals to 0. So we learned that this implies this only has solutions when? We actually need k is equal to n squared pi squared over L squared, right? And when k is equal to that, and they are what? We could say x sub n to indicate the n dependence. X sub n of x would then be sine of n pi x over L. Again, logically, that is me going through that three-step process for k0, k negative, k positive, and learning that only the positive k solutions allow for a solution to the boundary value problem, and those solutions are sines, and the k has to be n pi. And it has to be n squared pi squared over L squared because our beta had to be n pi in retrospect, in looking back. So, what did we find? Thus, we could construct u sub n of xt, which would have the form sine of n pi x over L, and then my time function e to the minus, what was k? We just figured out what k was, right? We just learned from the spatial function the k is not just anything. K has to be this guy, right? So e to the minus n squared pi squared over L squared times time. So this solves heat equation with, boundary condition as given. But there's one thing I forgot to tell you guys, right? Physically speaking, this problem doesn't quite make sense yet. What else would you need to know? Like, here's a hypothetical. Suppose that at time 0, the rod had a fixed temperature of 0 throughout its length. What would the solution then be? And by the way, we're assuming that this rod is insulated from the surrounding, so like there's no heat coming in from the ambient or anything like that. We're always assuming that there's some sort of insulator along the rod, and only interesting things happen at the end. That's our model. You don't need differential equations to answer this question. If you have an ice bath of 0 degrees at the end, if you start out at 0 degrees everywhere, this thing is just going to stay 0 degrees. If you've got no way to warm it up or for it to release, there's thermal motion at 0 degrees, right? Not absolute 0. So, right. What if on the other hand the temperature was, it was hottest in the middle, and then the temperature decreased to 0 at the edges, like a tent or something, if you were to graph the temperature? Well, then it would have a different solution, right? So the other thing I need to tell you is the initial temperature distribution. We also have to be given initial temperature distribution. Now, we haven't even needed to think about that so far. And that would be u of x comma 0 has to be f of x for 0 less than x less than L. I mean, this has to be, you have to be given this initial condition. Given an initial condition. So if you look at everything we've done, we have not fit the initial condition yet, have we? We haven't said anything about initial conditions. right? So this will fit. This will satisfy the heat equation for each n. It will satisfy the boundary conditions for each n, but it doesn't do anything about the initial condition, right? So then here's the jump, Fourier's leap, if you will. He had this idea that you could build the solution by taking a series of these guys. And let me just rewrite that in my exponential notation so there's no ambiguity. All of those things are in the variable, the argument of the exponential, if you will. Now, at least for the last time, I'm trying to, I try to come up with labels for these things for you guys so that you have a way of discussing them amongst each other. But what I will call this is the blank template solution. And the reason I call it the blank template solution is, and it's not quite right yet, because I need to allow myself to add as much of each one of these solutions for each n as I want in order to match initial conditions that I'm given. So I'm missing some coefficients in here. Typically, we'll use an a sub n there. So we can adjust, the idea is this, you can adjust the a sub n's to fit u of x comma 0 equals to f of x. This is given. Now you might wonder, Fourier, is this the same Fourier as of like Fourier series, right? The mathematics which is behind MP3 compression and other things like that. Yeah, it's the same Fourier. And let me show you why that is. What happens when we actually plug in 0 into our blank template solution? What do we get? U of x0 equals to what? The sum, n equals 1 to infinity, right? A sub n sine of n pi x over L. What happens with the exponential? Plug in t equals 0. E to the 0 is what? 1. So it's gone. And this is supposed to be equal to your given f of x. So what's this mean? This means if you can take f of x and you can write it by some mathematics as the sum n equals 1 to infinity of, say, b sub n sine of n pi x over L, then it's simple. Just set a sub n equals to the b sub n, and that ought to do it. Should solve the problem. All right? So the question is, for a given f of x, how do you actually find those b sub n's? They're called Fourier coefficients. Let me show you. So keep in mind that this f of x is a given, but for our purposes at the moment, arbitrary function, okay? So let's suppose it's possible. Suppose we can write f of x is equal to the sum n equals 1 to infinity of b sub n sine of n pi x over L. All right? What we do is something kind of sneaky. We multiply this by sine of f of x times, let's say, the sine of, let's say m. Well, m looks too much like my n. Let's say k pi x over L, right? And so what we're going to do is multiply by this on both sides. Like that. And then we're going to take that and we're going to integrate that from 0 to L. And we're going to do something a little bit sketchy for the integration. We're going to assume that we can pull that integration inside the summation, and we're going to integrate term by term. Now, analytically, that's nonsense, but we'll get away with it. Let's see here. I mean, there's some analysis to do here in a course we don't offer. I'm sorry, but anyway. Admittedly, the details of the convergence of Fourier series is a subtle and delicate, beautiful topic, which we don't exposit in any coursework here. Sorry. I can recommend books for you to read if you're interested. But I'm just assuming it's a kind of a natural leap to make, though, right? I mean, I'm bad-mouthing it, but really, this is probably what you'd try. And then the question is, how do you do this integral? Right? That brings us back to your homework. Problem 2 or 3, I think. All right? So the way to do that integral is to understand how to calculate, if we have sine of A times the sine of B, how do you do that? Well, here's how I do it. First of all, I would look in any of my calculus books, find out that all of my calculus books fail me because they fail to include the most obvious of interesting trig identities, because after all, it's only a 1,000-page calculus book. Why should it have one of the most important and interesting trig identities known to man? Now, in the calculus book's defense, it was written after the invention of Wikipedia, so you really don't have an excuse. But, you know, anyway, so convert sine and sine to imaginary exponentials, like so. And with that, we have 1 over minus 1 over 4 e to the I a plus b plus e to the minus I times a plus b minus e to the I a minus b, and then minus e to the I minus I a minus b. Sorry, I'll clean this up here in just a second. So then keep a half out front, and so that gives me a 1/2 e to the I a plus b minus e to the minus I a plus b minus 1/2 e to the I a minus b minus e to the minus I a minus b. And that is 1/2 oh man, plus. I was waiting for the sneeze, but okay, plus. So this is actually 1/2 of the cosine of a plus b minus 1/2 the cosine of a minus b. So there you go. This is the formula, the trig identity that gives you the product of sines in terms of a sum of cosines of the sum and difference of the angles. We can try it, make sure it works. What happens if we plug in a equals to pi over 2 and b equals to pi over 2? What should that give us? What's sine of pi over 2? 1, right? So if we plug in pi over 2 and pi over 2, we ought to get back 1, because 1 times 1 is 1. Does that happen? What happens here? Plug in pi over 2, we get, oh no. Uno momento. Look, and my check didn't work. I'm getting back -1. So I made a sign error in here.
Dropped a negative.
Where'd I do it?
Well, you want -1/4, and then you split it into 2 halves. There's no negative.
So I should basically keep the minus out front as a way to... I mean, there's various ways of... I think that the error is going from here to here. We should probably leave a minus out there is the simplest way to communicate the problem. And so I have a minus here and a plus here. You see, I was able to find that error by just plugging in known values. I try to, when I'm hurrying, check something. All right, anyway, going on. So this is actually, let's just focus on this integral, all right? So the integral of the sine of n pi x over L times the sine of k pi x over L dx from 0 to L is what? It's actually equal to 1/2, right? The integral from 0 to L of, I pulled the half out here, and we're looking at a cosine of what looks like n minus k, right? Times pi x over L, right? Minus the cosine of n plus k. Let me go on the other side of the curses. Stupid board. Parentheses n plus k pi x over L. Close my integration dx, right? So if you do those, I won't even write it out. What happens when we do those integrals? We get sines, right? And both of those. And when you evaluate those sines at 0 or L, what do you get? You either get sine of 0, or you get sine of an integer multiple of pi, because the L's cancel. So this is quite clearly 0, if what? There's an exceptional case here. If n is not equal to k. See, I need that when you actually go through the details here. Your u substitution gets an n over n minus k in the denominator, right? You got to think about like u equals to, think about u equals to this, right? So when you calculate du is going to be, you know, well, dx is going to be du times 2 divided by pi times n minus k. Well, that doesn't make sense if n is equal to k, right? So this argument I'm making that it's automatically 0 only is good if n is not equal to k. What happens when n is equal to k? We get integral sine squared pi kx, right, over L dx. And what's that equal to? One half of 1 minus the cosine of 2 pi kx over L dx, right? Now, again, for the reasons I was just describing, the cosine term integrates to 0 because it becomes sines under the integration, and sines evaluate to 0 under these bounds, so that piece dies. But the other piece gives us L over 2. So a nice way to communicate this is that this is actually equal to the Kronecker delta of n comma k times L divided by 2, which is just a convenient way of me telling you that that integral is 0 if k is not equal to n, and it's just L over 2 when k is equal to n. But what does that mean? That means that this infinite series is just what? B sub k times L divided by 2. Whoa. So what you mean to tell me is, yeah, that B sub k is just actually equal to 2 over L, the integral from 0 to L of f of x times the sine of k pi x over L dx. This is the formula for the kth Fourier coefficient. This is the formula for calculating kth Fourier coefficient in the sine series on 0 to L for f of x. Unfortunately, I don't have my book with me, but this is in chapter 10 of your book, and I think section 10.4 maybe. All right, there's several sections in chapter 10 devoted simply to the question of how do you find the Fourier decomposition of a function. The answer is you integrate the function with respect to appropriate sines or cosines. So let me recap. To solve the heat equation, subject to these the ice bath boundary conditions, given this initial temperature distribution, we find our blank template solution. And then we select these coefficients a sub n to be equal to b sub n, where the b sub n's are given by integrating the initial temperature function from 0 to L. And in so doing, we construct the solution to the heat equation. This is the Fourier technique. Any questions? I have an actual example to show you. This is, come on. You can turn off the lights. Eventually it'll show up here. I guess you better get them all at the moment until this thing heats up. It's sad. All right, come on. I'll let you decide when you can turn on half the lights, King. Let's see here. Anyway, so here we have a heat equation. You notice that I have annoyingly put, this means alpha's a fifth. Because the 5 is on the opposite side, I think. I had alpha times ut, right? So interpretation, the alpha is equal to 1/5 for this problem. My L is pi, which is wonderful. You like L to be pi. Why is that? In these formulas we were deriving, you got pi over L all over the place, right? If L is equal to pi, those are just 1. Super nice. And so here's the nth template solution like that. Again, the L and the pi cancel because L is equal to pi. So here's my sort of generic solution, b sub n sine of nx e to the minus 5, 5n squared t. And then I need to find the Fourier decomposition of 1 minus cosine 2x in order to solve this problem. That is not easy. Come on. Here it is, though. So we're trying to, so here we need to calculate 2 over pi, integral from 0 to pi, f of x sine of n dx. In this case, if you calculate for even n, this works out to 0, all right? Only the odd n is interesting. For odd n, in other words, n equal to 2k minus 1, we have the integral of this times that. And the details I'll omit here, but this works out to that. So that's your b sub k. Then I go back and I plug that in. And you might be like, it's important. I've got little b and big B. The point is, if I want to match this to this, I just make them equal. There's places later in the later problems where we find the Fourier decomposition of the function, but it doesn't have to match the solution exactly. There's like some extra thought process. So you might be like, why are you making this stupid step that they're obviously equal? Why don't you just say, plug this into there? Why are you making this step? Well, that'll become more obvious when we solve the other two problems, okay? But anyway, long story short, here's the solution to the heat equation. Here's my Fourier coefficient. That's my sine of nx, which is sine of n pi x over L with L equal to pi. And here's my time function. And that is the solution to the heat equation for that initial temperature distribution. I've got another one here. This one actually has, well, Well, anyway, I don't want to, I have a few more examples in the notes, but like next time we'll talk about the wave equation, all right? So you can turn the lights on. I think that's a good start. This method I used to solve the heat equation, it's the same, we're going to use pretty much the same method to solve the wave equation and Laplace's equation. It's always pretty much the same story. You fit boundary conditions, that gives you an infinite family of solutions, and then you use a Fourier technique to fit an initial temperature distribution, or for Laplace, an initial voltage distribution, or for the wave, actually initial position and velocity of the string. All right, well, we still have about 15 minutes for your homework, so go nuts.
I didn't have specific questions. I just wanted time to do it.
You wanted the whole class time to do it. Ah.
Yeah. And then if we had questions, we could ask these for 2 minutes.
So what you're telling me is I should end class early.
Yes.
So be it. Hit it.